In this section, I'll be explaining different types of computational model available for designing the prototype of the embedded system. Now, let us first understand what is a computational model. It is an idea to represent real-time process by deriving some mathematical equations that can be solved using computers. These equations are mostly derived from basic fundamental principles like conservation of mass and energy. Principle of conservation of mass states that neither the mass can be created nor destroyed. Now, to convert this principle to math equation, here is an example. Initially, let us assume that there is a 5 liter of water in a tank. Assume that there is a hole in the tank and the water is leaking through this hole at the rate of 1 liter per second. Now we need to calculate what is the mass in the tank. Obviously, it is the difference between the water in the tank and the water leaking out. That is, the water is going up at the rate of 4 liter per second. To solve this problem or to derive an equation for this problem to be solved using computer, let me consider a variables instead of a numbers. Let min be the variable that represents rate of mass going into the tank, and mout is another variable that represents the rate of mass going out of the tank. So the rate of change in mass is given by min minus mout, and the mass conservation principle is given by rate of change of variable is equal to the differentiation of the variable with respect to time. That is, d by dt of m equals min minus mout. This is how we derive a simple math equation that can be solved by writing a program. Now, in the same example, let us try to know how the temperature in the tank changes. Now, consider the temperature of the water in the tank is 80 degrees Celsius and the water going into the tank is at the temperature of 20 degrees Celsius. This mass equation alone cannot derive the temperature equation in the tank. To derive an equation for this, we need an additional equation called energy equation. This can be solved by getting more information about the system. This is where the concept of modeling plays an important role. To get more information from the system, we need to solve more equations, which makes the system more complex. So, to ease the complexity of the system, different types of computational modelings are used for implementing or designing an embedded system, and they are data flow graph, control data flow graph, state machine model, sequential program model, concurrent or communicating process model, and object-oriented model. Now, let me explain the first type of modeling, that is data flow model. DFT illustrates how the data is processed by the system in terms of inputs and outputs. As its name indicates, its focus is on the flow of information, where the data comes from, where it goes, and how it gets stored. DSP is one of the typical embedded system example that can be implemented using DFG. Now, let me consider an application that contains in computational requirements like x equals a plus b and y equals x minus b. This can be represented using DFG model as shown in the diagram. Here, the circle in the diagram represents the operation that has to be performed on the data A, B, and C. And the arrow mark represents the data flow or the data path. If the circle is having an incoming arrow, then it is called as an input data. If the arrow goes out of the circle, then it is called as an output data. Generally, the DFG model is of two types, acyclic DFG and non-acyclic DFG. In an acyclic model, there is no multiple inputs or output values, whereas in case of non-acyclic, the output is fed back to the system as an input data. The second type of model is controlled data flow graph or a diagram. This model is similar to the DFG, and here the data flow is controlled by some conditions. This model consists of both the data operations and the control operation called as decision maker. Now, let me take an application that contains an conditional requirements as follows. If flag equals 1, x will be a plus b, else y is equal to a minus b. These requirements can be implemented using CDFG model as shown in the diagram. And here the decision maker is represented using a diamond symbol. And according to this, if flag equals 1, then addition operation on the variable a and b is performed. Else, subtraction is performed on the variable a and b. Now, the third type of modeling is state machine model, which is also called as an SMM model. The state machine model is used for modeling reactive or event-driven embedded systems whose processing behavior is dependent on state transmission. Embedded systems used in the control and industrial applications are the typical examples for the event-driven systems. This model consists of four components to describe the behavior of the system, that is, states, events, actions, and transitions. The state is a representation of the current situation. An event is an input to the state that stimulates the state transition. Transition is the movement of the system from one state to another. Action is an activity to be performed by the system. The SMM model is also called as FSM or a finite state machine if the number of states in the system are finite. To illustrate this type of model, let me consider an example of seat belt warning system. Here, in this example, an alarm is used to trigger the event. Initially, the alarm is in the off state. When the vehicle ignition is turned on, the system changes to the waiting state and remains in that state for 10 seconds until the driver or the passenger puts the seat belt or ignition key is turned off. When either of these events happens, the system moves back to the alarm off state. This happens within 10 seconds. At 10 seconds, the timer expires and the system changes from waiting state to the alarm on state, where the beep sound is heard for 5 seconds. And then the system moves to the alarm off state if the timer times out or seat belt is on or ignition key is turned off. Whichever happens first, accordingly the state or the system changes from the alarm on state to the alarm off state. The timer that is used in this application can also be modeled using FSM. Here, initially the timer is in the idle state and the timer goes to the running state when it is loaded with the count value. From the ready state, the system moves to the running state and remains in this state until the timer expires, that is the count value reaches 0 or if any interrupt occurs. Another example I would like to discuss that can be implemented using FSM model is automatic tea coffee vending machine, and it is represented as shown in the diagram. This application or model consists of 4 states: state A, state B, state C and state G. State A is called as wait for coin state. State B is called as wait for user input. State C is dispense tea. State D is dispense coffee. Initially, the system will be in state A, waiting for the coin to be inserted by the user. Once the user inserts the coin, the system changes from state A to state B and waits in that state for the user input. The user input can be either cancel, tea or coffee. If the user presses a cancel button, the coin is pushed out and the system changes from state B to state A. If the user presses tea or a coffee button, then the system makes a transition from state B to either state C or a state D, where the coffee or a tea is served to the user. Once it is done, again the system goes back to the state A and waits for another coin to be inserted to trigger the events. All these words, tea dispense, tea button press, coffee, the insert coin, cancel button, all these are called as events. Based on the events, some actions will be taken. The next example that can be implemented using FSM model is the public telephone unit. This application consists of 9 states. State A is called as a ready state. State B is wait for a coin. And state C is wait for a number. State D, dialing. State E, call in progress. State F, call terminated. State G, unable to make call. State H, invalid number input. State I, out of order. Initially, the calling process is initiated by lifting the receiver of the telephone unit. After lifting the phone, the user needs to insert a 1 rupee coin to make a call. If the line is busy, the coin is returned on placing the receiver back on the hook. If the line is through, the user is allowed to talk till 60 seconds, and at the end of 45th second, it prompts for inserting another 1 rupee coin for continuing the call as initiated. If the user doesn't insert another 1 rupee coin, the call is terminated on completing the 60 seconds time slot. Now the system is ready to accept new call request when the receiver is placed back on the hook. The system goes to out of order state when there is a line fault. The next type of modeling is sequential program model, whose function or the processing requirements are executed in sequence. And we are taking the same automatic seat belt example, seat wearing belt as an example to implement using sequential program model. And sequential program model is represented using the flowchart and is as follows. When the vehicle ignition is turned on, the system waits for 10 seconds and then checks for ignition on. If true, then checks for seat belt on. If true, ends the process. If false, the alarm will be set for 5 seconds and starts making the beep sound. During this course or process, the system checks for the timer expires. If no, then checks for the ignition state or seat belt status. If true, then it stops the alarm and ends the process. The last type of modeling is concurrent and communicating process model. This model is used for synchronizing and executing various processes by using different types of communication techniques like shared memory, message passing, or events. It is basically used for concurrent execution of the various tasks or functions in an application. Again, explain this concept, we are using the same application, seat belt wearing system. Accordingly, the tasks in these applications are divided into 5. Wait timer task, ignition key status monitoring task, seat belt status monitoring task, alarm control task, alarm timer task. These 5 tasks cannot be executed randomly or sequentially. We need to synchronize their execution through some mechanism. Initially, the alarm starts only after expiration of 10 seconds wait timer and along with the seat belt off and ignition key on. Hence, alarm control task is executed only when the wait timer is expired and if the ignition key is in the on state and seat belt is in the off state. These scenarios are well explained in the wait timer event associated with the timer task event. And the events will be in a reset state initially and will be set when the timer expires. Similarly, the events ignition on and ignition off are associated with the task ignition key status monitoring and also the events seat belt on and seat belt off are associated with the task seat belt status monitoring. The events ignition on and ignition off are set and reset respectively when the ignition key status is off. Similarly, the events ignition on and ignition off are reset and set respectively when the ignition key status is on by the ignition key status monitoring task. On the same line, the events seat belt off and seat belt on are set and reset respectively when the seat belt status is off. On the other hand, the events seat belt off and seat belt on are reset and set respectively when the seat belt status is on by the seat belt monitoring task. The events alarm timer start and alarm timer expires are associated with the alarm timer task. The alarm timer start event will be reset initially and it is set by the alarm control task when the alarm is started. The alarm timer expires will be in a reset state initially and it is set when the alarm timer expires. This alarm control task waits for signaling of the event wait timer expires and starts the alarm timer and the alarm if both the events ignition on and the seat belt off are in the set state. If not, alarm control task simply complete its execution and returns. If in case alarm is started, the alarm control task waits for the signaling of any one of the events, alarm time expire or ignition off or seat belt on. Upon signaling any of these events, the alarm is stopped and the alarm control task simply completes its execution and returns. This concurrent method is commonly used for modeling real-time scenarios. The last type of model is object-oriented model, where the functions in an application are represented using the object. The object consists of mainly the functions and the variables defining the applications. All the objects for the given applications are derived under the same class name. And also, this model uses the concepts like inheritance, data abstraction, hiding, and protection. Thank you.